In this video, let us understand flying wedge representation and its conversion into Fischer projection and Fischer projection back into flying wedge representation. So first of all, what did we speak? The carbon atoms are tetrahedral and tetrahedral groups are 3D. Always representing these 3D molecules in 2D is difficult. So we use some representations like wedge representation, or we use some projections like Newman projection, etc. So let us understand this wedge representation. So this carbon atom has 4 groups, one CHO group, one CH2OH group. These two are represented by simple lines. So this carbon atom and the CH2OH are in one straight line or are in one plane, that is the plane of the board. One OH group is outside the plane of the board, one hydrogen is into the plane of the board. Let us see the same with the molecule with an example. So let me make it first OH and H. So this will be CHO and CH2OH. Let us see it this way. So this group that you are seeing here is CHO group. This is the plane of the board. So this is the central carbon atom and CH2OH group is here. The group towards you is represented by the solid wedge, that is this wedge. So this group is OH group and that is represented by dashed wedge is hydrogen, which is into the plane of the board. This is the plane of the board. So this hydrogen is into the plane of the board and this OH is outside the plane of the board. These two are in the plane of the board along with this carbon atom. Now what we are doing is, just for a representation, we are doing a rotation. Where am I doing the rotation? The rotation is along this axis. This axis is passing through CHO. So the axis is like this. You can imagine the axis passing like this. Along this axis, I am doing a rotation. So how would I do the rotation? The rotation is such that this hydrogen that is present, should come outside. So previously hydrogen is here, all of you look carefully. So this hydrogen that is here now is carefully coming out. So I did a 180-degree rotation, you may see it that way. The hydrogen that is here now has come here. So the hydrogen has come out. So the OH which is previously here has come in this direction. I should not call it 180. The OH that is present here is coming out in this direction. So again I am doing the rotation. There was a OH here. This OH is coming here. So the hydrogen inside is coming outside. Now look at the groups. There is a CHO at the top and there is a CH2OH in this direction, which is now pointing inward. Both H and OH are pointing towards you. Now what am I doing is, I am doing a tilt to this molecule like this. Understand this representation. I am doing a tilt such that this CHO and CH2OH, both of them are in one line. They are in one line. See, they are in my line. So this is CHO and this is CH2OH. Now when you look at this molecule, two groups are outside. If this is the plane of the board, two groups are outside and two groups are inside. What are the groups that are outside? H and OH. That is why they are represented by solid line. What are the groups that are inside? That is CHO and CH2OH. That is why they are represented by dashed line. So you can see this is the plane. Two groups are outside, two groups are inside from this plane. So this is this representation. Now what we have to see is, we have to see the 2D representation of this. Suppose light falls on this molecule like this. Then there will be a shadow that is casted on the plane of the board. So in that shadow, what is going to happen? All these groups, H and OH, though we are representing by a horizontal line, they are outside the plane of the board. Whatever we are representing by vertical line are into the plane of the board. So you can note that if they are in vertical line, this is vertical line, they are into the plane. And if they are in horizontal line, this is horizontal line, then those groups are out of the plane of the board. What is in the plane of the board? Only this carbon atom that you are seeing is in the plane of the board. So groups that are on horizontal plane, now these two are represented by one horizontal line. It is easy to write on paper, so that is why I am representing by a horizontal line. These two are, we are representing these two on a vertical line. It is easy to again represent on paper. This is the plane of the board. This is the central carbon atom. This is the plane of the board. So a complex 3D molecule we have written in a simple line format. This line format is what we are calling as Fischer projection. That is converting a wedge dash into Fischer projection. If you want to take the Fischer projection and convert back into wedge dash, you can mentally reimagine the whole process. So groups that are on the horizontal plane, imagine them to be outside like this. So this will be H and OH. Groups on the vertical plane, imagine them to be inside like this. After doing this, H and OH, now what you have to do is you have to make a conversion. Now this molecule is the molecule in wedge dash representation like this. Now after this, you have to do a rotation. How are you going to do the rotation? Put two groups on one plane. Now CHO and CH2OH are in one plane, and H and OH are in the other plane. So one group goes inside, one group goes outside. So this will be a convenient representation to the molecule. So this is how you are converting Fischer back into wedge representation. So wedge representation, lines, Fischer representation lines, converting into wedge, then converting into flying wedge in the case, that is the original wedge where two groups are in the line of the board. So this is converting Fischer and wedge mutually into each other. This is the 3D representation. Once we get this view, you have to mentally think about few other molecules and try to do the conversions. So once you get a practice of it, you will be able to repeat the processes easily, whatever representation is given. Now let us see one more, you can say, convention here. Whenever we write a Fischer projection, we always ensure that the most important functional group generally lies in the vertical line. H and OH or the lesser important functional groups should be on the horizontal line. If only one carbon atom is there, try to write the most important functional group at the top. That is how we have started our convention, so all the molecules are like this. So here CH2OH and CHO. CHO is the important functional group. So that is why write it in the vertical line, that two at the top. CH2OH at the bottom. H and OH will be on the horizontal lines. That is a convention. So suppose if I take another molecule like tartaric acid, it has two chiral carbon atoms. This is one chiral carbon atom, this is one chiral carbon atom. So here most important functional group is COH. So I am writing them on the vertical lines. Other groups I am writing on the horizontal lines. So that is the convention for writing Fischer projection. Next, we also have one more representation as D and L. Initially, when they found that certain compounds are optically active, they have to classify one as positive isomer, one as negative isomer. So for that they have taken a simplest chiral molecule which is easily available as the reference molecule. That molecule is glyceraldehyde. What is glyceraldehyde? Whatever we are seeing is glyceraldehyde. Glyceraldehyde is CHO, CH2OH, OH and H attached to one carbon atom. All four are different groups, chiral carbon atom. So we are taking this glyceraldehyde. Now when you write the Fischer projection of glyceraldehyde, if I am writing the OH to the right and H to the left, such glyceraldehyde is called a D-glyceraldehyde, which I am representing by plus. I am representing by capital D, you can see that. The mirror image of this Fischer projection will actually have, this is OH close to the mirror, so the OH will be close to the mirror, H is far away from the mirror, H is far away from the mirror, so this is H. So in this Fischer projection, OH is to the left. If OH on the chiral carbon atom is to the left, then I am calling it L-glyceraldehyde. So this is D-glyceraldehyde, this is L-glyceraldehyde, which I am representing by minus. Now these two compounds are not the same. Earlier I spoke about the term called enantiomers, which are mirror images and non-superimposable. So this molecule is not exactly that molecule, it is non-superimposable. For example, this is CHO and this is CH2OH. One molecule is OH on this side, H on this side. Other molecule is OH on this side and H on this side. So these are the two different molecules. So if you really want to convert one to another, you can't do any rotation. You have to break the connection and remake the connection. Only then you can make one into another. Since all four groups are different, first molecule is not superimposable on the second molecule and they are mirror images of each other. This fall under the category of enantiomers. So one is D, one is L. So the wedge representation of L is going to be like this. You have to imagine now. OH is outside, OH is outside, H is outside, H is outside, CHO inside, CHO inside, dash line, CH2OH inside, CH2OH inside by dash line. The wedge representation of D-glyceraldehyde we have already written. This is the wedge representation. Like this, these two are different representation. So you can mentally imagine taking this and placing over here. Now CHO falls on CHO, CH2OH falls on CH2OH. But on H there will be OH, on OH there will be H. So because of this reason, these two are non-superimposable. This is the representation of different Fischer projections and converting into wedge. Always remember, even though if more chiral carbon atoms are there, glyceraldehyde becomes the representative molecule. We always compare with glyceraldehyde. For example, if I am taking this molecule, this is the bottommost chiral carbon atom. Always look at the bottommost chiral carbon atom. In the bottommost chiral carbon atom, OH is to the right. So in one chiral carbon atom, if OH is to the right, you have to compare that with the bottommost chiral carbon atom. So this compound will be D. So if I want any compound of this, only one representation is this OH should be on this side. You may get a doubt, what if both the OH are to the left? This is also L, this is also L. There are other names. There may not be only enantiomers. There can be other type of compounds called diastereomers also. We'll speak about that subsequently. Now, the bottommost chiral carbon atom is the reference. You are comparing with glyceraldehyde. Here the bottommost chiral carbon atom is to the right. Then it is D-glyceraldehyde. Here the bottommost is to the left. This is also L-tartaric acid. Here also bottommost is towards the left. This is also L-tartaric acid. This is D-tartaric acid. That is the difference between D and L. Also these are the conversions to Fischer and wedge. Hope this point is clear related to the conversions and representation of D and L.